In this video, we are going to continue our work in section 4.3, Fractional Exponents. In particular, we have 3 examples addressing these 2 objectives. Basically, it's solving equations using roots. We will use our Texas Instrument calculators in this video, so if you don't have it already, please get your graphing calculator. All right, so basically, we're starting here and saying, let's solve our value. In order to solve this equation, basically we have to go through and get rid of the 3.2 power. We have to get rid of this exponent. And we have seen previously that if we had something like x squared equals 100, how did you get rid of an exponent of 2? We would take the square root. And it's a notation that we don't typically write, but we always took the second root. So this is an idea that if we want to take the 3.2 exponent and get rid of it, well, if you ever want to get rid of exponents, you are going to take roots. And whatever root you want to get rid of, you would take 3.2. So this, of course, begs the question, how could we use our calculator to speed up this process? Specifically, when we are looking at our calculator, we can see right here above the x squared button that we have a button for square root. But we don't have a button for 3.2 root. Fortunately, there is the process that you would have learned about in Algebra 2. In particular, one of the main exponent rules we're going to take advantage of, if you have an exponent raised to an exponent, that's the shortcut. Yes, the shortcut is to simply multiply those 2 exponents. Of course, it's good that you remember that because this is the main tool that we would have. If we want to get rid of a 3.2 exponent, we raise it to another exponent also. We will raise it to the 1 over 3.2. Because when we do this, we would have 3.2 times 1 over 3.2. And what happens to those exponents? They turn into just 1, so we'd have x to the first. And x to the first is, of course, just plain x. Now, all the stuff that I'm writing down is, of course, way more work than you're actually going to write on your paper. You're not going to write down every single tiny little step like this. When you are solving the problem, x to the 3.2 equals 1,000, you should write down and show that you're taking it to the reciprocal power on both sides. Then we would also know those exponents essentially cancel, giving us just x equals blob, and this is the thing we'll type into our calculator. So we'll come and you say 1,000 to the 1 over 3.2 exponent. I would like to point out we are using the TI-84 plus silver. And the programming on this one naturally gives us the exponent. If you are using a different style calculator, you may need to take and put, with other calculators that don't have this programming, you may need to put the exponent inside parentheses, such as 1 divided by 3.2. And again, it doesn't really show up well on this calculator, which is why. All right, so I pulled up one of the older Texas Instrument calculators. Here's the TI-83 Plus. And so for this one, I can type it in, 1,000 to the 1 over 3.2. And this is where I'd like to caution you. With the older style calculators, They follow the order of operations, and so this is going to take to an exponent of 1 divided by 3.2, and we're getting something drastically different. To make certain that the reciprocal is kept inside the exponent, you will need to insert parentheses around the exponent to make certain that it turns out the same. Obviously, I'm using this to say, know your calculator and make certain that you can actually use it correctly. However, we're still not finished with this one, because we have been given an answer of 8.6596, so approximately 8.66. But when we go into our y equals and solve this graphically, no, I just have the two sides of our equation. When we graph this, we can see that there are actually two solutions because it intersects twice. There is still a limitation to your calculators, even our 84 plus silvers. You must be aware that frequently you will wind up having two answers. And it's the same reason that we talked about yesterday. Whenever you take an even powered root, you will wind up with the positive square root or the negative square root, and basically just be careful that you're paying attention for those two potential solutions. For this particular one, we do get the 8.66, but it will wind up being positive or negative values. Okay, so let's move on to solve this exponent, to solve this equation. What would you do? How do you get rid of the exponent? To get rid of exponents, you will raise it to another power, but take the reciprocal power, 1 over. And this will give something that we can then put into our calculator. 800 to the negative 1 over negative 4.3. So 800 to the 1 over negative 4.3. And with our programming, we get 0.21128. So rounding to 3 significant digits, we obtain 0.211. Thus, we obtain a solution that we would have m is equal to 0.211. And the last example to finish up this video, solve this thing. And you're looking at it right now and saying, holy, that's a significant step up in complexity. Well, keep in mind, anytime we try to solve, we have inverse reverse, we have zero product rule, quadratic formula, or we have guess and check. One of the reasons the last two problems were so straightforward, there was a single occurrence of the variable. So it was an inverse reverse type problem. Just undo the exponent. That was the key focus behind example 6 and example 7, seeing how to undo an exponent. This one clearly is not an inverse reverse type problem. What strategy is it? Does the zero product rule apply? I'm hearing one answer for yes. A key feature that you would want to recognize, and in fact, one really important part, 1 minus x on the left part, and we have 1 minus x on the right part. That tells us we can factor out the common factor of 1 minus x, and this will set up the zero product rule. Likewise, the square root here is referring to the single square root. We could rewrite this square root of x as x to the 1/2 power. And then we could also recognize that we have an x to an exponent. We have x to an exponent. And so we have these things that will also factor out. I also like to rewrite this further and say 3 halves written that way. If I write 3 halves this way, it might be easier to recognize that we have a factor of 3 and a factor of 3. So there are a lot of things in common which we can factor out and set up the zero product rule. All right, so let's actually set up the zero product rule and factor out the pieces they have in common. Factor out the 3 that they had shared in the blue. We can factor out the x which is shared in red. What exponent should we take? We have the exponent of 1/2 here on the left. We have the exponent of 3 halves on the right. Which exponent should we take? Please remember, you always take the smaller exponent, the one that's farther left on a number line. And since 1/2 is smaller than 3 halves, we'll take out x to the half. Factoring out the piece that they had shared in the yellow, what exponent do we remove for 1 minus x? All right, so taking out each of the pieces that they have in common, we now have to look at the giant blob of what got left behind. It's kind of cool that I had it color-coded because a lot of it then is still in the black. If we take out the 3 in the blue, we leave behind the half. We took out x to the 1/2, and we took out 2 of those instead of all 3, which means if we took away 2 of them, 1 of them was left. On the right-hand section, the 3 is gone. We removed 1/2 of the 3 halves, which leaves behind x to the 1 power, or just plain x. And we likewise took out both of those. So here's our blob that's left. Now, for the sake of simplicity, I'd like to combine our like terms and simplify this stuff. So start by copying down all the pieces that I'm not working with. And let's make some observations. 1/2 times 1 is just a half. 1/2 times opposite of x is minus x over 2 minus x. Well, if I wanted to get a common denominator between all 3 of these, I can get a denominator of 2 and recognize then that this entire blob simplifies down to 1 minus 3x all over 2 equals 0. All right, so now that we've set up the zero product rule, we can start applying it. We'd have 3x to the 1/2 is equal to 0, or 1 minus x quantity squared equals 0, or 1 minus 3x over 2 equals 0. Now, just in the effort of saving some time, I'm not going to go through and do all the algebra to solve these. If you're watching a pre-calc video, you probably know how to solve simple inverse-reverse equations like this. This one gives us x equals 0. This x is equal to 1. And this last one, x is equal to 1/3. Thus, we've obtained our 3 solutions, and we've finished. That completes our video for this particular topic for the solving equations.